Good morning. My topic is application of symmetry arguments to particle reactions. Symmetry is in nature. Many objects in nature presents a high level of symmetry indicating that the forces that produce to these objects feature the same symmetries. Learn structure of nature by studying symmetries it features. What is a symmetry? It is a transformation that leaves an observable aspect of a system unchanged. The unchanged quantity is called an invariant. Example: any rotation of the needle of a clock changes the orientation of the needle but doesn't change its length. The length of a clock needle is invariant under rotational transformations. Physics law can also be left invariant under transformation of symmetries. For example, Coulomb's law giving the electric force of two charged particles on each other, which is given by F is equal to K Q1 Q2 by R square, where K is the constant known as Coulomb constant, Q1 and Q2 are the charges in coulombs, and R is the distance between the charges. Symmetries. Symmetry arguments have a long and honorable history in physics, but only in recent times they have come to dominate our understanding of fundamental physics. The power and beauty of such arguments became fully apparent only when expressed in mathematical form. What precisely do we mean when we say that physical laws display symmetry? A square is symmetric when rotated through 90 degrees around its center. This operation produces an orientation identical to the initial one. We say that a symmetry operation leaves an object invariant. A circle is left unchanged or invariant by a rotation through any angle. An object is said to be symmetrical when there are operations on the object that could have changed its appearance but in fact do not. Similarly, physical laws also have symmetry. One of the basic principles of physics is that the laws of physics at one location are the same as at another, and at one time the same as at another. This principle is equivalent to a symmetry. The laws of physics are invariant when we change our viewpoint, either from one location to another or from one time to another. The symmetry of interactions. All current attempts at finding the laws of nature use symmetry. Symmetry is described mathematically by groups which often have cryptic names. The standard model is classified as U1 into SU2 into SU3. Each symmetry is associated with a conserved quantity such as energy, momentum, or charge, which is known as the Noether's theorem given by M.E. Noether. What is U1? U1 is a symmetry group of the electromagnetic interaction. Here, one implies fermions act as singlets. One fermion, which is electron. One boson, it's a photon. What is SU2? SU2 is a symmetry group of the weak interaction. Here, 2 implies fermions act as pairs or doublets. 2 fermions, neutrino and electron. 3 bosons, Z, W plus and W minus. SU3 for color. SU3 is a symmetry group of the strong interaction. Here, 3 implies fermions act as triplets. 3 fermions, red quark, green quark and blue quark. 8 bosons, 8 gluons. Here each gluon connects 2 quarks with 3 colors each. Implies 3 into 3 is equal to 9 combinations. Here white is excluded. Therefore 8 bosons is equal to 9 minus 1 is equal to 8 gluons. SU5 for unification. Unification attempts to treat all interactions as one with the same coupling constant and the same symmetry group. The most popular symmetry group for unification is SU5. A grand unified theories, or simply GUT, unifies all three interactions of the standard model at high energies where the coupling constants approach each other. Gravity is still left out because of it is so weak. Our best bet for incorporating gravity is string theory. Symmetries. Symmetry of a quantum field SU2 SU3 is known as gauge symmetry. Symmetries of space-time. Translation in space implies x tends to x plus a. Here A is continuous. Time reversal implies T tends to minus T. Plus or minus is discrete. Supersymmetry, boson changes to fermion and vice versa. Symmetry of a quantum field or gauge symmetry. All current quantum field theories are gauge symmetric. Each interaction has its own symmetry group. U of 1 implies electromagnetic, SU2 is equal to weak, SU3 is equal to strong. The conserved quantity of a gauge symmetry is a charge, like electric charge, isospin, color, etc. Symmetries of space-time. Here there are three symmetries in space-time, which are continuous symmetries, discrete symmetries, and supersymmetry. In continuous symmetry, translations, rotation in space-time, momentum, energy, angular momentum are conserved. In discrete symmetries, C is equal to charge reversal, P is equal to inversion or parity, and T is equal to time reversal occurs. Here, C is equal to charge reversal means particle change to antiparticle and vice versa. P is equal to inversion or parity means XYZ changes to minus X minus Y minus Z and vice versa. T means time reversal, which implies T changes to minus T and vice versa. Supersymmetry. It is extra space-time coordinate with A dot B is equal to minus B dot A. Here boson changes to fermion and vice versa. Supersymmetry, the last untapped space-time symmetry. Each fermion is teamed up with a boson as super partner and vice versa. Since none of the non-particles are super partners of each other, one expects new particles with high mass. Super partners could appear at the LHC, particularly the neutralinos, fermion partners of the photon, Z and Higgs. The lightest neutralino is a top candidate for a WIMP, a heavy particle explaining dark matter. Convergence of coupling constant with supersymmetry. Coupling constants are not constant. They change with energy and approximately converge onto a single unified coupling constant. Supersymmetry predicts a new set of supersymmetric particles above 1 tera electron volt. They change the energy dependence of the coupling constant. Now the convergence is improved and the unified coupling constant is close to the symbol number 1 by 8 pi. Symmetry breaking. Although we have all these nice symmetries, they are often only approximate. One says that the symmetry is broken. It appears that nature always tries to get away with breaking the symmetry as much as possible without violating the most basic principles of physics like relativity, causality, etc. Discrete symmetry breaking. The weak interaction breaks the symmetries C, P, and T. Charge reversal symmetry, or C, requires equal amounts of matter and antimatter, but our universe consists mostly of matter. Inversion symmetry P is broken by a different treatment of left and right-handed particles. The standard model contains only left-handed neutrinos. The CPT theorem states that the combination of CPT should be preserved for very general reasons like relativity. This has been verified at the level of 90 parts per trillion by comparing the E by M ratios of a proton and antiproton. Minimal symmetry breaking. The Higgs field breaks the SU2 symmetry of the weak interaction in order to create mass. The symmetry is broken in a rather subtle way. The laws of physics are symmetric, but our universe is not. For example, Maxwell's equations do not favor any direction. This rotational symmetry is broken by a magnet, such as a compass needle, which points in a particular direction. Many benefits of symmetry are preserved because the laws of physics remain symmetric. Symmetry breaking by the Higgs field. The Higgs field does not choose a particular direction like a magnet. It chooses a particular average value. All other fields oscillate around zero. The figure shows Higgs field and all other field. The non-zero average of the Higgs field produces the molasses effect that create the mass of particles. The anthropic principle. The concept of minimal symmetry breaking can be pushed into the realm of philosophy. Suppose that many universes exist which all obey the same laws of physics. Each of them breaks the symmetry in a different way and thereby creates different particle masses and coupling constants. Some argue that our universe must have coupling constants that allow humans to exist and ponder the laws of nature. For example, the sun can be too hot or too cold for life. This is a slick excuse for our inability to predict the many parameters of the standard model. The most important of them is the electromagnetic coupling constant alpha. For values of alpha slightly smaller or larger than 1 by 137, the sun would be too hot or too cold for life. Thank you.